Okay, so this is Secret Key Encryption, Lab Activity 8 by Antonia Lemency. Our first task is frequency analysis against monoalphabetic substitution cipher. So this is our table. So we check the frequency. W is the most frequent. We assume that CIW is equivalent to Z since W is E. And this is what happens when we replace C with T, I with H, and W with E. TH DT is that, replacing D with A. ASE is R, replace S with E. So type became dose, replace Y with O, replace T with S. Gath is path, replace G with P. Zos is whose, replace Z with W. Seep becomes keep, replace X with K. Wants equals ways, replace N with Y. With becomes with, replace V with I. Blessed becomes Kesu becomes blessed, replace Q with B, and replace O with L, and U with D. Rsake becomes forsake, U. So then for this we found out person rejoices, my and me must come from the following group of letters. Person rejoices, my and me. So that's why we replaced PHBR with NJCM respectively. And lastly, by analyzing all the remaining words, we can say that KJL must be replaced by G, V, and Z. Okay, and then both F and M are not present in the ciphertext, so they cannot be determined. So anyway, for task 2, encryption using different ciphers and modes. So this is the text that we're going to encrypt. So 3 encryption methods is the BF-CBCA encryption. So that's what happened. So what you see there. Next is we did the seed CBC encryption and the RC2 CBC encryption. Okay. Now for task 3, it's encryption mode, ECB versus CBC. So it was encrypted using AES 256 ECB and AES 256 CBC. To view the image, the header is appended to the encrypted messages. So this is via AES 256 ECB. All right, and if we compare that with AES 256 CBC, okay, so we can see that A shows us traces of the original image, as you can see, so we can still see it, right? And then B shows little to no trace of the original image, which is good, okay? And this shows that AES 256 CBC is better than using the AES 256 ECB, which makes it easy to deduce the image, okay? Task 4 is padding. So only ECB and CBC use paddings. OFB and CFB both do not use padding since they use a block cipher as a stream cipher. Okay. XO are the plaintext and output of the block cipher. So using the AES 256 ECB encryption, right? And this is with the 256 CBC encryption. And this next is the OFB encryption and the CFB encryption. Okay. And now you can see we had 3 files created. And the screenshot below shows the creation of the files containing 5, 10, and 16. Okay. So the 3 files are encrypted using a method with padding. So in this case, we use the ECB method. And we decrypt the resulting files with the -nopad option so that the padding will still be there. And we can see that the padding is a repeated value. It is appended because the file must be a multiple of the block size 16. All right, next is error propagation, corrupted ciphertext. Okay, so as you can see that's the task 5. All right, quick brown fox jumps over the lazy dog. All right, so the file is it's 1,000 bytes long, then encrypted. So we encrypted the file using the AES 128 cipher. And we can see that a single bit of the 55th byte in the encrypted file got corrupted. And that's why we used the bless hex editor. Okay. And we decrypted the corrupted ciphertext file using the correct key, right, and IV. So that's what you can see here. So that's ECB on top, CBC on the bottom. And next is OFB. All right, OFB and then CFB. And so from this, you can see that there's a noticeable difference between each encryption method. Right, ECB and CFB had both their first and second line corrupted. So if we're going to look at it, ECB, right, and CFB, that's the first line, and second line corrupted. But the parts of the message are still readable. So as you can see, CFB, you can still read quick brown fox, like especially in the third line. ECB also in the third line, right? ECB was affected in a certain portion between the first and the second line, while in the CFB, the corruption was spread throughout the first two lines. So you can see that as compared to this, right? And in CBC, we observed that the first two lines were also corrupted, but there's a change in the spacing of the lines, right? As part of line 1, merged with line 2, and then again in line 3, the corruption was almost gone, right? So that's here, right? CBC. However, if we look at OFB, we can see that it suffered the most damage, right? It's from the corruption, as pretty much the entire file was rendered unreadable. So that was it for lab activity 8. Alright, I forgot to include this part, sorry. But this is task 6, encrypting the plain text using different IVs. So as you can see, there's the two plain text that we use, different IVs, as you can see. Alright, there's a different, they're not the same, okay? And when we encrypted them using the same IVs, as you can see, there's no difference with the first encryption and the second encryption, right? So that means, basically it means that the IVs must be unique, because encrypting the same text will result in you'll have different results basically, right? Next is we got C2 over here, so this thing, okay? And so given from P1 above, so that's this, right? So we can convert that into hex. So this is the hex number that we got, right? So basically, I just wrote that here, okay? And essentially, when we XOR this value with C1, we get this value, which is the key. And if we use that key and XOR it with C2, that's when we'll get this. And this is basically which is order launch a missile. So that's just a bit for task 6. Thank you.